There are millions and millions of chemical reactions, and in order to try to keep them all straight and understand what's going on, scientists put them into different groups with similar reactions in the same group. That's called classifying chemical reactions. Classifying chemical reactions can help you to understand what's happened in a particular reaction, and it can sometimes help you to predict what's going to happen if you know what the reactants are. So we're going to use a system in which there are 5 different types of reactions: combination reactions, decomposition reactions, single replacement reactions, double replacement reactions, and combustion reactions. Most reactions will fall into one of these 5 categories, but it's not a perfect system. Not every reaction fits perfectly into one of these categories. Still, it helps us to keep reactions straight and to figure out what's going on and predict what's going on a lot of the time. In a combination reaction, 2 reactants combine to make a single product. So in this particular case, magnesium combines with oxygen to make magnesium oxide. If you're looking at an equation that has and just trying to decide if it's a combination reaction, you're looking to see if there is one product, and in this case there is. That one product is always a compound. The reactants can be elements or compounds. The one product is always a compound. Here's an analogy to a combination reaction. Person A on the left and person B also on the left are alone with a plus sign between them. When they get together, they make the couple AB. And there's just one couple that's the result of this reaction. In a decomposition reaction, you start out with one chemical compound, and it gets broken down into 2 or more simpler substances. In this case, mercury 2 oxide is decomposed to make mercury, the element mercury, and oxygen molecules. If you're looking at an equation and trying to decide if it's a decomposition reaction, you're looking to see if there is one reactant, and in this case there is. That one reactant is always a compound. So here's an illustration of a decomposition reaction. On the left, the orangish substance is ammonium dichromate. When it's heated, that's what's happening in the middle picture, it decomposes. And if you look at the picture on the right, you might think that there is only one product, that gray substance. That substance is chromium 3 oxide. But in fact, if you look at the equation above, you'll see that there are 2 other substances: nitrogen, which is a gas under most conditions, and so you can't see it in the picture of the products, and water. And water, when it has been heated, is also a gas, so you can't see it in this particular product. But this one substance, ammonium dichromate, did break down into, in this case, 3 simpler substances. And not all of the simpler substances are elements. In fact, 2 of them are compounds in this case. In a single replacement reaction, an element and a compound turn into a different element and a different compound. So notice that in this case, the zinc is combined with copper 2 sulfate. The zinc replaces the copper in the copper 2 sulfate because zinc is more active than copper, and you end up with copper and zinc sulfate. You start out with an element and a compound, you end up with a different element and a different compound. Here's an illustration of this. On the left, the fellow in the orange shirt is all by himself, and there's a couple there that's dancing. The arrow, after the arrow, the fellow in the orange shirt has replaced the guy in the right shirt and is now dancing with the girl in the picture. And presumably that happened because the fellow in the orange shirt is more active than the guy in the white shirt. He seems to be able to dance fancier. We started off with a single individual and a couple. We ended up with a different couple and a different single individual. This is an analogy to a single replacement reaction. In a double replacement reaction, two ionic compounds at the start exchange their positively charged ions, their cations. The positively charged cations are the ones at the beginning of the compound. So in this case, the potassium replaces the barium, and potassium joins the chloride ion, and the barium at the same time replaces the potassium, and the barium ends up with the carbonate ion. So potassium carbonate and barium chloride turn into potassium chloride and barium carbonate. Here's another illustration of a double replacement reaction. In this case, the spheres represent atoms. We start out with two compounds, magnesium oxide and calcium sulfide. Both of these are ionic compounds. The magnesium ions and the calcium ions, which are the positive ions, change places. Magnesium replaces calcium and forms magnesium sulfide. Calcium replaces magnesium at the same time and performs calcium oxide. Two replacements going on at the same time, double replacement reaction. In a combustion reaction, we start out with a hydrocarbon, a compound that contains carbon and hydrogen. It combines with oxygen, and the products are always carbon dioxide and water. A combustion reaction can also start off with a compound that contains carbon, hydrogen, and oxygen. It still combines with oxygen, and the products are still carbon dioxide and water. So the equation on the bottom shows a compound, C2H5OH, which has oxygen in it. It reacts with oxygen to make carbon dioxide and water. That's a combustion reaction. Here's this reaction illustrated in this picture. Carbon atoms, the carbon atom is the gray sphere. Hydrogen atoms are the yellow spheres, and oxygen atoms are the red spheres. You can see that the hydrocarbon, the CH4, combines with oxygen molecules. The oxygen combines with carbon to make carbon dioxide. Oxygen also combines with hydrogen to make water. Again, this is a combustion reaction. 5 kinds of chemical reactions: combination, decomposition, single replacement, double replacement, combustion. Over and out.